Hello, everyone. Formally welcome you to the first seminar of the Permafrost Network series for 2024. And Astrid would be presenting her research work on climate change-induced increase in the maintenance cost for Yukon highways for a time frame from 1994 to 2022. A brief introduction about Astrid. So she completed her master's at Carleton University in September 2023 under the supervision of Dr. Chris Byrne, and she was working on highway infrastructure sustainability and adaptability in Yukon. Prior to this, she completed her bachelor's degree in environmental science from the University of Ottawa in 2019, where she became increasingly interested in the study of permafrost. Her thesis examined the cost associated with the effect of climate change and permafrost on the highway infrastructure maintenance in Yukon. Throughout her studies, she was able to engage in the northern fieldwork and collaborate with several stakeholders. Post-graduation, Astrid moved to Whitehorse, Yukon, where she now works in the transportation planning for highways and public works. Here, navigating the challenges presented by permafrost, she's excited to contribute to the informed decision-making using the knowledge and experience acquired through her academic journey. So Astrid, I hand over the stage to you, and you can formally start your presentation.
Thanks so much, Usman, for the introduction. So again, my name is Astrid Schetselaar, and this past September, I completed my master's thesis at Carleton University in the Department of Geography and Environmental Studies under the supervision of Dr. Chris Byrne. So my project was part of a larger collaboration between various departments at Highways and Public Works, including collaboration with the engineering branch, planning branch, and maintenance branch in the department. But my project specifically looked at the changes in historical highway maintenance costs that are associated with climate change. So this project was further supported by NSERC PermafrostNet, as well as the Northern Transportation Adaptation Initiative at Transport Canada. So I'll be presenting some of the key findings of my thesis, and hopefully we'll have plenty of time for questions afterwards. So I'll be starting out giving a brief overview of climate change for Yukon specifically, and some of the work that I was part of and was recently published in the journal Arctic, which compares previous climate projections that were used in engineering design and the actual observed climate for the region. I'll then be introducing some of the main research objectives and principal methods used to accomplish these, and then present results for the entire highway network, and then show some more specific examples for specific highway corridors. And then finish off the presentation with kind of the main takeaways and conclusions. So climate records for Yukon date back to 1897 for Dawson, around 1940 for Whitehorse, and 1985 for Old Crow. So this kind of just represents the southern Whitehorse, kind of central Dawson, and northern Old Crow temperature data. So these are shown in the figure here with the annual mean temperature for these locations, with the line showing the running mean for the previous 10 years of data. We can see here that air temperatures have begun to increase since about the 1970s, and the rate of increase is accelerated at higher latitudes. Over this 50-year period, warming has been just under half a degree per decade at Whitehorse and Dawson, and over half a degree at Old Crow. The rate of warming is also most pronounced in the winter months, with rates around a degree per decade at each of these locations. So these rates of change have been projected over time using different simulations of climate to predict what kind of temperatures we can expect in the near future. So part of the work that we did is to look at a total of 29 climate scenarios from 7 climate models from the early 2000s for Yukon that were used in engineering design, and kind of compare these to the actual observed climate to see whether projections have over, under, or estimated or are consistent with the current climate for the territory. So presented here with the dashed line are low and high projections of future annual air temperature, and then shown with the solid line is the actual mean observed temperature of 30-year averages for both Whitehorse and Dawson. So the first normal here starts 1941 to 1970, with the most recent normal being the 1991 to 2020 normal. And then all the projections were made relative to the baseline of 1961 to 1990. So we can see that for both regions, the annual warming recorded has been consistent with kind of the upper projection, with Whitehorse increasing by 1.2 degrees Celsius and Dawson by 1.4 degrees Celsius since the baseline. But then if we kind of look at the most recent 10 years of that last climate normal, we can see that warming is even greater, with temperatures actually exceeding what was projected. So we also looked at the same comparison for mean winter temperatures for both Dawson and Whitehorse. And warming here has actually exceeded the highest projection, with Whitehorse increasing by 2.5 degrees and Dawson by 2.8 degrees since the baseline. And again, if we look at the mean winter temperatures for the most recent 10 years, warming is even greater, with an increase of 3 degrees for Whitehorse and 3.6 for Dawson. So similar analysis was also conducted to look at precipitation trends in Yukon, which are shown in the figure here, but these trends in historical precipitation are not very clear. That's mainly due to the high spatial variability in this index, and for Yukon in particular, this is very difficult as the terrain is so dissected and there's very few climate stations with sufficient records in between. It is expected, though, that the precipitation regime in the north will shift with temperature. For example, warming in the shoulder seasons would result in changes in the form of precipitation, with snow being replaced by rainfall in both spring and fall. Predictions have also been made for increases in snow mass with increasing humidity. So an example of this change can kind of be seen in this figure here, which is a normal probability plot with the magnitude of August and September rainfall plotted against the probability of exceedance for a 60-year period. So in a normal distribution, each 20-year interval should contribute 6 to 7 events to the upper, middle, and lower distribution of the graph. However, for Mayo, there's actually an overrepresentation of recent August and September rainfall totals, with 11 out of 20 of the most recent years in the upper third of the distribution. So this data might suggest that there's a change in the precipitation regime currently taking place. Yes. So what all these observed and predicted changes mean for highways that are built in Yukon in permafrost environments? So one of the first steps in starting our work was kind of to get acquainted with road conditions and challenges within each highway corridor. So we traveled across the entire highway network to gather these insights, consult with the foremen at various maintenance camps, and highlighted some of these experiences in this short informational video. Hopefully it works.
Almost half of Canada sits on permanently frozen ground, or permafrost. Permafrost can be defined as earth materials that remain at or below 0 degrees Celsius for at least 2 consecutive years. However, as climate change continues and air temperatures rise, the once permanently frozen ground begins to thaw. In the Yukon, much of the road infrastructure is underlain by permafrost, and much of it is ice-rich, which means that as the ice in the ground melts, there's a loss of volume beneath the road and causes the ground to consolidate, leading to the development of sinkholes and deterioration of the road surface. In the north, where the extent of transportation network is limited and more vulnerable to disruption, climate change-induced impacts on the system can lead to disruptions to supply chains and passenger flows, which have many economic, social, and cultural consequences for Northerners. This means that to ensure transportation networks remain safe and reliable, roads will require increased maintenance to meet functional standards.
So after we journeyed across the entire network, we started kind of deciding some of these main objectives for this research. So the main objective was to essentially provide a retrospective analysis of historical maintenance costs that are associated with climate, and with this financial monitoring approach to kind of determine the vulnerability of existing highway infrastructure to climate change. So secondly, the objective was to try to further link maintenance costs to physiographic characteristics to determine if there was a varying response of the terrain to climate change. And these characteristics include superficial conditions, glaciation, permafrost distribution, and specific climate conditions at regional scales. So in order to accomplish these objectives, first we did kind of an extensive background investigation, which involved looking at these different physiographic regions and their characteristics. We also looked at superficial deposits, glacial history, permafrost distribution by zone of relative coverage, and ground ice abundance. And then we also gathered specific climate data, including precipitation and temperature, for kind of a representative station for each physiographic region. For the cost analysis, I examined the entire financial ledger of historical operation and maintenance expenses for a total of 28 fiscal years, so starting in 1994 all the way to 2022 for all maintenance camps in the network. So each maintenance camp is kind of shown in these black squares here, and they're mainly in communities, but some are just the maintenance camp itself on the road. So all of these were examined except for Old Crow up here, just because it wasn't actually connected to the highway network. The research also only examines expenses for highways specifically and does not include any expense for community or resource roads. And these were also included in the financial ledger I received, but only highways were looked at for this research specifically. The data also needed to be mapped between two periods, as there was this coding change in, I believe, 2018. So you can see an example of the most recent code here, which kind of breaks it down by each component. But there was actually a different coding system used prior to this. So we kind of had to map all of these activities so we could create this continuous data set. The expenses were also converted to constant dollar values through an inflation adjustment. So all the values you will see later are presented in 2021 constant dollars. So from the maintenance cost database, there were 4 maintenance activities which were identified as being climate related. The first is snow removal, which includes both sanding and drift control. And these activities may increase due to the predicted increase in snow mass, but can also increase due to more extreme weather, such as heavy snowfall and storms, which cause these snow drifts. The second is icing control, also referred to as glacier control in the local database. And this activity deals with the sheet-like buildup of ice that forms due to overflow and seepage from groundwater, springs, or below river ice. This is an activity which is most common in discontinuous permafrost at the foot of hill slopes. And icing development may increase due to a longer freeze-up and increases in precipitation, but the development are also highly based on other local site conditions. The third is culvert activities, which include kind of clearing of the culvert, repairs and reshape of ditches, but not actually replacing a culvert. This would be in the capital budget and not in the maintenance budget. And this activity may increase due to the need to accommodate higher stream flows as precipitation and heavy rainfall increases. Lastly, the activity of clearing of landslides and repair of embankment washouts. This category is common in ice-rich permafrost areas, particularly near hill slopes and near rivers, and may be initiated by heavy rainfall, forest fires, erosion, or a blocked culvert. And this is an expense which is often of high magnitude, but occurs on an intermittent basis. So we don't actually see this expense in every single year, but when we do see them, they are quite significant. I also wanted to note that the costs that were examined here are primarily associated with hydrologic processes and not actually directly related to permafrost thaw due to temperature increases. The activities that were related to the deterioration of the road surface, which could be associated with permafrost thaw, and subsidence is typically treated by reconstruction or capital costs and wouldn't be shown in the maintenance budget. So we did not analyze those. Routine surface maintenance, such as grading, patching, and crack sealing, are also difficult to separate from normal activity and are kind of contingent on wear and tear from traffic volumes. So we did not look at those in this study. So I'll first start to present the results for the entire highway network as a whole, and then present some of the examples of maintenance expenses for individual regions. So I want to start off by presenting the total operation and maintenance costs for the entire network. which is shown in this plot on the right here. And these numbers are again adjusted for inflation. So they're about $28.4 million per year in the first 5 years and are about $25 million in the last 5 years of data, with actually a decrease over time of about $30,000 per year. So in these pie charts, we can also see that camp overheads, which includes any kind of cost to keep a maintenance depot running, have increased and actually become a bigger proportion of the total budget, leaving less resources for actual activities. Camp over expenditures also differed quite significantly between camps, which are in remote communities or within kind of larger communities. For example, in Mayo, they were only about 300,000, but for Eagle Plains, they were over 1 million. So we actually removed these costs, so they won't be presented in the pie chart over the next couple of slides. So this plot on the left shows the increases in climate-related costs, which is the total for, again, those 4 activities: snow removal, icing control, culvert activities, and the repair of slides and washouts. And we can see here that on average, these expenses increase from about 7.1 million in the first 5 years of the series to about 11 million in the last 5 years. This is equivalent to an increase of about $175,000 per year over the 28-year period, but when looking at the last kind of 15 years, this rate has been about $285,000 per year. We also looked at the total climate-related costs as a proportion of the total operation and maintenance budget. So that's shown in the figure on the right. And this was kind of to examine and illustrate the increasing impact that climate-related expenses specifically are having on the budget. So in 1994, these climate-related expenses were about 25% of the budget, and this has doubled to about 50% in the last couple of years of data. So in these pie charts, we can see kind of the average breakdown of these costs for both periods, with each climate-related activity in color, and then the gray kind of represents all the other maintenance activities, but again, this does not include the camp overheads. So snow removal was the largest increase by about 18% between 1994 to 1999 and 2017 and 2022. Culvert activities and repair of slides and washouts increased from about 1% to 3%, and icing control remained at the same percentage. So overall, we can again see that climate-related expenses are taking up a much larger amount of the budget, and again are leaving less resources for other O&M activities that may be also just as important and are actually needed to create kind of highway infrastructure that is resilient to some of these effects. We also do see here that the total operation and maintenance expenses, so that's just this value in the center here, decreased from about 28.4 million to 23.4 million between both periods. So it's just important to note that these estimates of change are higher than the actual dollar amounts. So these plots kind of show the cost of each individual activity since 1994, with the dashed line showing the rate of change for the entire period, while the dotted line shows the rate of change since about 2005. So the rate of increase for cost of each activity has varied, but again, snow removal has consistently increased at about $142,000 per year since 1994. There is no kind of apparent increase for icing control expenses, but when we do look later on, I'll show some examples at kind of these individual regions, we can see that for some roads, these costs have actually substantially increased, but decreased in others. Culvert activities have increased slightly at an overall rate of 4,000 annually, but increased by about 28,000 since 2005. It is important to note, though, that these activities have been highly impacted by legislation. For example, culvert activities can actually only be performed in a short time window to limit impacts on fish species, and several permits are required to perform the work. Then lastly, the repair of slides and washouts also increased during this time, but again, this activity incurs kind of these large intermittent costs, so they do not actually follow linear relation, even though there is a linear relation plotted here. For example, these events incurred a total of $2.5 million in 2012 and 2013, but the costs were only about $75,000 in 2018. But overall, these activities have kind of increased in frequency and magnitude in the last 15 years. So while we kind of analyzed the data by section, we could see that there's kind of dominant climate-related expenses that varied region by region based on kind of inherently distinct physiographic characteristics, which means that there could also be a variation in the terrain response to a changing climate. So we therefore decided to conduct a further in-depth analysis of costs by 7 physiographic regions. So they are just listed here. The first is the Shakwack Trench. So this is pretty much the North Alaska Highway from Haines Junction to Beaver Creek. Then the next region is the Coast Mountain regions down here. And this includes the Haines Road as well as the southern end of the Klondike. Then the Southern Lake section is from the Alaska Highway from Whitehorse to Watson Lake, but also includes the Tagish and Atlin Road. Then we have the Liard-Ross Lowland region, which extends from Watson Lake all the way to Drury Creek. The Lewis Plateau, which is the Klondike from Whitehorse to about just south of Stewart Crossing. Then the Central Yukon Plateau is the North Klondike Highway, as well as the Silver Trail. And then lastly, the Ogilvie Mountain Eagle Lowland region, which is essentially the entire length of the Dempster Highway. So I'll just show 2 examples of these regions. So first, the Shakwack Trench. The highway itself in this region is closely situated to the slopes of the Kluane Ranges of the St. Elias Mountains, but travels in a region known as the Shakwack Trench. This trench is typically 4 to 8 kilometers wide and predominantly covered by glacial and colluvial material, including till, gravel, sand, and silts. Between Burwash and Beaver Creek, over 80% of the road is underlain by permafrost, which is typically ice-rich. This is also where we see the Dry Creek site. We can see here again that the expenditure profiles, that climate-related expenses make up a much larger percent of the total in the last 5 years of data, particularly here for Destruction Bay, where the highway is so close to these hill slopes. Culvert activities and slides and washouts make up a much larger percent of the total. So these plots again show the rate of increase, which varies kind of by these 4 camps that make up the North Alaska Highway, with the highest in the Destruction Bay maintenance camp and the lowest in Haines Junction. Then moving on to the Dempster Highway, which is in the Ogilvie Mountain and Eagle Lowland region. And here we can see kind of very distinct expenditure profiles with different climate-related expense emphasized at each camp. So we can see here that in the Klondike section, which is just the first bit here, the highway is again situated near the base of slopes in discontinuous permafrost, where icing development is common. So that's shown in the green in these pie charts here. The landslides and washouts occur most frequently in the Ogilvie section and actually make up about 14% of the budget in the last 5 years. So this section again is close to hill slopes, close to rivers, where slope failures and erosion, particularly in ice-rich permafrost, occur more frequently during the thaw period, as large volumes of meltwater and limited infiltration of the frozen ground can initiate such washouts and slides. Then finally, in the Eagle Plains region, the highway kind of traverses these rolling hills where activities such as landslides and washouts and culvert activities are a bit less common. And this main activity here is snow removal, which makes up half of the budget. And so this activity is mainly associated with snowfall, unobstructed winds in a tundra environment above the tree line, where snow drifts often accumulate and often force road closures. So again, here showing the 3 different maintenance camps, with Eagle Plains increasing at about $12,000 per year. And at Ogilvie here, you can see these large magnitude costs, which are these landslides and washouts. So to kind of summarize this information and to show which regions have become more costly, each region is kind of normalized for comparative purposes. For snow removal expenses, we normalized by kilometer. So we can see that for all regions, the cost per kilometer has increased, but some more than others. For example, the Coast Mountain region, which is the Haines Road and the south end of the Klondike, have remained at a relatively high cost of just over $5,000 per kilometer. We can see that 4 out of these 7 regions have almost doubled in cost, with the largest increase in the central Yukon Plateau, which is again the Silver Trail and North Klondike Highway. We have actual snowfall data, which can be attributed to some of these differences. So again, in the Coast Mountain regions, there wasn't actually an increase in snowfall. So that's why we don't see this super large increase, but in Mayo along the Silver Trail, snowfall actually increased by about 50 centimeters between the 2 periods. For icing control, we instead kind of calculated the percentage that each region contributes to the total icing control cost for the whole network. So this may help indicate which regions are most susceptible to these impacts. Increases have primarily been in the Lewis Plateau and Central Yukon Plateau region, which again corresponds to the North Klondike Highway, Silver Trail, and Campbell Highway near Carmacks. So what these regions kind of all have in common is that they are located in discontinuous permafrost, where 50 to 90% of the landscape is underlain by permafrost, but there are these kind of unfrozen zones within the ground that enables and concentrates groundwater movement and allows it to move throughout the year. So here's the breakdown for culvert activities, with almost half of the resources for this activity spent on the North Alaska Highway. So here, the Shakwak Trench. However, it may be possible that kind of increased efforts were focused in this highway corridor specifically and might not actually be indicative of the actual need to accommodate higher stream flows as precipitation and heavy rainfall increase. Additionally, other activities which indicate drainage problems, such as a culvert replacement, which would be shown in the capital budget, could be more indicative of what if there are any actual problems related to climate change. So the highest cost for slides and washouts were in the Southern Lakes region. So this is the Alaska Highway from Whitehorse to Watson Lake, as well as the Dempster Highway. So these high costs are likely, again, associated with increasing occurrence of heavy rainfall, proximity to steep slopes, degradation of permafrost, and close proximity to the river. However, such costs may also indicate that there's an inadequate capacity of drainage systems that are currently in place for these regions. So in the last 10 to 15 years, many of the climate stations have kind of specifically stopped recording rainfall and snowfall. So therefore, in order to associate maintenance expense with climate variables, we had to use total precipitation. But we did see an increase in the days with winter precipitation across the network, and they were statistically significant with snow removal expenses, except for in the Coast Mountain regions, again, where this index remained consistently high. Similarly, a relation was determined for slides and washouts and summer rainfall, and we did actually see a relation between the highest summer rainfall recorded in the same month as the highest slide and washout expense. However, we didn't detect any trend in icing control and autumn rainfall, but this may be due to the variation in the duration of the freeze back, which we did not look at here. So although there's some evidence that climate may be forcing these increases in expenses, I also wanted to quickly acknowledge some of the other causal factors which may explain increases in costs over time. So for example, adherence to maintenance standards, which are either due to kind of formal regulations or due to kind of the public's informal expectation, can increase costs. A camp foreman may over or under exceed certain expectations to meet asset management objectives. There may be an increase of public pressure over time for higher safety standards and kind of a faster return to driving conditions after a disruption. There could also be cost increases that are associated with aging infrastructure and equipment. And finally, like most studies, there may be also errors in data entry. For example, hours may be charged to the wrong activity, or capital expenses are recorded as O&M. So the final step of my project was to kind of evaluate the differences in climate-related expenses between highway sections that are underlain by the 4 categories of permafrost. So the maintenance activities that I've looked at here are kind of indirectly influenced by permafrost, but are primarily driven by hydrologic processes in a permafrost environment. So the activities that were looked at here only include these icing control and repair slide and washout costs, and does not look at snow removal or culvert activities. So the map here shows the results of an overlay analysis conducted for highways and the high resolution permafrost distribution model by Bonaventure et al. The model actually only extends to about the 65th parallel, but from other maps, we assumed that north of kind of Ogilvie here, that it would be in continuous permafrost. So we determined that about 13% of the network lies in continuous, 44% in extensive discontinuous, 34% in sporadic, and 9% in isolated patches. The maintenance costs that I mentioned earlier, which are associated with the presence of permafrost, have been the highest for extensive discontinuous, as well as quite high for continuous. And when we look at this on kind of a per kilometer basis, highways with more than 50% permafrost are kind of twice as costly than in those with lower permafrost presence. So with that, I'd like to conclude my presentation with the 4 key takeaways of my thesis. First, climate-related maintenance expenses are increasing across the entire highway network in both absolute terms and as a proportion of the total cost. So they're actually eating up a larger percentage of the budget. Second, expenses in each physiographic region are associated with the physical characteristics of these regions. Third, on a per kilometer basis, maintenance activities influenced by permafrost are twice as costly for highways underlain by more than 50% permafrost than in sections with lower presence. And lastly, the variability observed across the network indicates that the response to climate change in terms of these maintenance expenses kind of varies throughout each region, and that perhaps hazard assessment and management will need an approach at the scale of these maintenance sections. With that, I want to thank everyone for attending this webinar and open the floor to any comments or questions.
Thank you very much, Astrid, for such a nice and elaborate presentation.
Astrid, your total values, the ones where you show that in general costs are increasing, how sensitive are those to your inflation assumptions? You turned everything into 2021
Yes.
constant dollars, right? And when you did so, you end up with this slope.
Mm-hmm.
Now, if you make different assumptions about how things have inflated over the last 25 years, you might actually end up with a slope looking somewhat different, either higher or lower. Did you test that to see how your assumptions affected that, or was it under all circumstances did it show the same trend?
Well, we tried it as well without even using inflation, and we could still see this increase. But then obviously with the inflation adjustment, there was a larger increase.
A very interesting study. So I don't think I'm trying to, I just wondered about that question. The second question I had, your last conclusion, which was about how the extensive discontinuous zone is possibly the most expensive. Mm-hmm. There's a nice, easy sort of physical explanation for that, which is that in that zone, you've probably still got permafrost beneath the highways and it's degrading. So all makes sense to us as permafrost scientists and engineers, which is great. But I was thinking about the distribution within those permafrost zones of highways which are asphalted versus highways that are gravel surfaced. And were you able to tease out whether there were any differences between expectations, for example, of snow removal on the Dempster versus the Alaska Highway? I just wondered whether that mattered or not to any of your calculations.
Yeah, so we did kind of look at this idea of like different surfaces for the road, whether it's gravel, pavement, BST. But kind of the activities that we looked at aren't so much affected by what type of surface the road actually is. There are obviously kind of different functional classifications of these roads that do kind of have different standards. Like, for example, the Whitehorse section obviously has a quite high standard, so snow removal is quite quickly after a snowfall event. And then, for example, the Campbell Highway, which is a lower class of road, would actually have less snow removal activities. So we didn't dive too deeply into that, but did keep those kind of questions in the back of our mind.
Okay, thank you, Astrid.
Yeah.
Hi, Astrid. I just have a question about culverts, and you kind of partly answered it already, but I'm just wondering how much detail there was in the work orders or reports on the nature of the work, as far as is it because it's not draining sufficiently for the hydrological conditions, or is it because the culvert became bent because of settlement under the road, or is there anything like that mentioned in those?
No, there was not too much. It would just be like a budget line item that was all grouped under culvert activities. So even reshaping of ditches was kind of this activity that was clumped together under culvert activity. So it was difficult to kind of know what the actual issue was. But I suspect that perhaps in the capital budgets, there would be more details as to what's actually going on with the culvert, but did not get a chance to look at that here.
Thanks. That was a great presentation.
Thank you.
Okay, I'll ask one more. So at the start, you showed the ground ice map and talked about physiological regions and the relations, and then the relation between permafrost zones and the costs. So, I mean, I can kind of see the link between, in the continuous permafrost zone, it's relatively high, and the ground ice is modeled as higher there. But was the ground ice mapping at that scale, given the scale of the kind of problems that are being fixed, and the fact that they're not, several of them aren't ground ice related necessarily, was the ground ice information at all useful, or was it kind of just a guide that went along with other information on physiographic regions?
Yeah, it was definitely just used as a guide. We looked at kind of more specific on-site ground ice conditions for kind of specific sections, but it was still kind of interesting to look at where the highway kind of is underlain by these ground ice conditions. But it's a map that's at the scale of the entirety of Canada, so just look at it from the scale of just the territory. It was more used as a guide. Yeah.
Cool. Thanks.
I can ask one question basically. So in the initial slides, when you were showing those temperature trends and then precipitation trends, so what was the source of that data that you showed there? And in the last 10 years, you also showed there's a huge increase in temperature. So is it based off some local stations, or what's the source mainly for that one?
Yeah, so it's all data from Environment and Climate Change Canada. So we collected this for pretty much all the stations in the Yukon, but then we kind of chose these representative stations, so Whitehorse and Dawson. And then we also did this kind of similar analysis for the Northwest Territories, where we looked at several stations there. But yeah, so we had this kind of, because these projections were made relative to this 30-year baseline, that's why we showed the increases by these 30-year normals. But I just wanted to show kind of just only looking at this average of the last 10 years, how much greater the temperature is, which wouldn't necessarily be reflected in this 30-year normal.
And then with regards to the maintenance work that is being done by the government of Yukon, so are you, in the future predictions, basically, are you looking at these, so the analysis that you have done for the past years and projecting it on to the future, or you're looking for other resources as well, for how do you predict that, okay, this region, as it has been consuming more cost per kilometer for the maintenance, so you're because in the next budgets you would be calculating, or you would be accounting for that. So are you only solely based on this data, or you're looking for other resources for the maintenance? Like, for example, some research. I'm basically asking this question because my own project is somewhat related to future predictions of like highway changes or the linear infrastructure changes. So that's what I was asking.
Yeah, so I haven't too much tried to kind of look at projecting the maintenance costs into the future, just because the governments are kind of capped at a certain budget, and it depends on what your budget is every year. So you can't just start projecting this when there's actually going to be a cap on it every single year. So that's kind of the issues that we saw there. But yeah, it would definitely be interesting to see kind of how much more these climate-related expenses are kind of eating up the budget and leaving not leaving as much money for actual other activities, which are just as important to keep the highways up to good condition.
Thank you very much, Astrid, for such a nice talk.
Thank you.
I would also like to invite everyone who's present for the next seminar that is being held on 1st of May. It will be by Andrew Clark, who will be presenting on the advancing Arctic coastal erosion measurements and monitoring through the UAV, SFM, and object-based image analysis. So you guys are most welcome. It would start at 10 a.m. Western time, like the Vancouver time, at the same time, basically, as it was today. So thank you very much for being present today and attending this talk. And thank you, Astrid, again.
Thank you so much.